Hello everyone, I'm Bashima from UNC Chapel Hill, and today I'm going to talk about our work Zygarde, time-sensitive on-device deep inference and adaptation on intermittently powered system. Tiny intelligent computers are everywhere. They have entered into our bodies, our homes, and inside our life. Their goal is to sense and infer interesting events to make our life more efficient, productive, enjoyable, and healthier. These tiny computers are powered by batteries, which comes with the inconvenience of periodic maintenance, which can be bulky and are extremely harmful for our environment. Alternative to batteries is to harvest energy from sources like solar, kinetic, and RF. Energy harvesting technology enables deploy and forget type sensing and inference applications. Timely execution is needed in this tiny computer to allow proper action in time. Because the amount and the availability of harvestable energy is uncertain, it is extremely difficult to ensure timely execution of tasks running on these intermittent computing devices. A task that is schedulable in persistently powered system may miss deadline when the energy is intermittent. In order to execute this task in intermittent system, we may use approximation. If we divide each task into mandatory and optional portions where executing the mandatory portion in time is acceptable, we can schedule it in intermittently powered system. Deep neural network is a layered architecture where the output from a layer goes as the input of the next layer. We exploit this layer architecture for imprecise computing. We choose DNN for representation learning and cluster-based classifier for modeling. The deeper layer of DNN provides more complex representation that gives better classification accuracy than the shallower layers. We introduced Zygarde, an energy and accuracy-aware real-time task scheduling framework that flexibly executes compressed DNN tasks in intermittent system. It is based on two observations. First, we observed that all real-life data are a combination of easy and hard samples. Here we have a classifier which identifies sound of rain, faucet, and cat. The representation at the first layer of DNN produce overlap clusters, but in the second layer, the clusters are further apart. However, the audio of cat is distinct enough from the rest to be identified in the first layer. So, cat is an easy sample, whereas rain and faucet are harder samples. Next, we observe that the energy generated by a harvester is bursty and the state of energy generation is maintained over a short period. We propose a probability metric called eta to determine how predictable the system is. Higher eta indicates similarity to persistent system, whereas lower eta means the predictability is low. To allow impreciseness in Zygarde, each DNN layer with corresponding classifier is a unit, and we terminate execution when the utility of future units are low. We need to define this utility and derive the utility test with minimal overhead to decide when to terminate. In traditional imprecise systems, the mandatory and optional segmentation is done at compile time. As the boundaries varies for each data sample in DNN, we propose a lightweight solution that calculates imprecise boundaries at runtime. We call this threshold-based utility policy. On the left figure, the closest centroid to the data point, which is a triangle, is the orange one, and the second closest centroid is the blue one. As the distance delta 2 and delta 1 are very similar, the system is not confident whether the sample belongs to the blue cluster or the orange cluster. Thus, the utility of executing the next layer is high. On the right figure, this difference between delta 2 and delta 1 are significantly large. So the classifier is more confident that the sample belongs to the orange cluster and does not need to execute the next unit. We propose the difference between this delta 1 and delta 2 as the utility of each future unit. We evaluate the utility-based early termination policy on 4 datasets, but here I'm only showing the result for ESC10. Though we have reduced the inference time using this policy, we take a hit in the accuracy, which is not acceptable. To improve the accuracy, we propose a layer-aware loss function, which is inspired from contrastive loss. It tries to maximize the distance between samples of different classes and minimize the distance between samples of the same classes at each layer. Using layer-aware loss, we improve the accuracy by more than 4%. Finally, we propose a priority function that schedules this dynamic imprecise task based on deadline, utility, impreciseness, and eta. When the energy is unpredictable or the energy generation is low, we behave conservatively and only execute mandatory portions. When the system is predictable and the energy generation rate is high, we execute both mandatory and optional portions. Here we show the performance of the scheduler using priority function, and we are showing all the 4 datasets we have done evaluation on. We compare it with EDF and a variant of EDF which only execute the mandatory portion and called EDF mandatory. We see that Zygarde schedules similar amount of tasks as EDF mandatory but achieves higher accuracy. This way, we achieve better performance and introduce impreciseness in deep neural network, which can be used for real-time scheduling in intermittent system. That's all from me. Thank you very much for listening, and I'll be taking any questions.